My name is Jackie Faherty, and I'm a senior scientist and senior education manager at the American Museum of Natural History. It is a telescope that was launched and sent off about 1 million miles away from Earth to a Lagrange point, to a stable point in the Earth-Sun-Moon system. And it's imaging the sky to do one very, very important thing. And that is to measure precisely the positions, the motions, and the distances to stars. Now, this is why this is so important. I think that this is the most important catalog that humanity has ever been given. So all of the laws of astrophysics, all of the laws of how we know what the universe is, where it's going, even where the Earth's place is within it, is based upon a foundation on one really important thing, and that is how far away things are. What is the distance scale? And so we basically got an idea of this once we figured out that the Earth's round and that the stars are far away, and we started measuring how far away they were. We started to unlock what the stars looked like, how stars moved, how stars' brightness changed, that we lived in a galaxy, that galaxies were these things that existed and other things were farther away. And everything up until 1 year ago was locked in on distances that had come from the Hipparcos mission, another European Space Agency mission. So all of the laws of stellar astrophysics and cosmological rules were also set on 120,000 stars that had their distances measured. And that was a lot of stars then. Gaia, 1 year ago, April 25th, 2018, unveiled their catalog of 1.4 billion distances. That's part of why this is such a big deal. We just upped our understanding of distances, which, if you are buying what I'm telling you, it's the foundation of understanding the universe. Now the game of doing science is cracked open in a way that is blowing every astronomer's mind. It's almost like every single astronomer needs to redo their PhD thesis based on these new numbers that just came in. There is no question in science, in astronomy, that was asked prior to April 25th, 2018, that doesn't need an update because this catalog came out. That's why it's so important. There's several things that can come out right away. One of the easiest ones that I love to bring up is what got unveiled with not just three-dimensional map, but three-dimensional map with motion. So you know the directions that stars are coming from and you know where they're going. And that is actually really important. So first you can see, let's start at home. What you can learn is the rate that stars fly by your sun. So how many times does a star fly through our solar system? It's actually something I didn't even think about before Gaia. I just thought it was something that we could guess at a number based on the density of stars that we kind of see around, but that it shouldn't have been that big of a deal. Turns out it's a big deal. In the past million years, every million years, the number that just recently came out of a great new science result of Gaia is that within 3 light years of the sun, closer than the closest star, so the closest star is roughly 4 light years away, within at least 3 light years, you get 19 plus or minus 2 flybys that just toss themselves through our system. And that's furthest approach at 3 light years. A significant number actually fly closer. In 1 million years, we're going to get a flyby within 16,000 astronomical units, or well within the Oort cloud, so well within our solar system. It's going to fly right on by. It's a K-type star, probably carrying with it its own solar system and its own Oort cloud and its own Kuiper belt. Yeah, so I'm also arguing like we need to study that system so well right now, because if you want to visit another solar system, it's coming. It's on its way. It's going to fly within 16,000 AU. That's not so bad. Voyager and Pioneer are on their way out there. Like, we've got the opportunity to catch stars as they fly by. If humans stick around for another million years, this is going to be a really exciting event. Mark your calendar. So that's one thing, stellar flybys. Another thing, just thinking on that same scale, when you look at the motions, is the history of the Milky Way galaxy at large. And I actually loved this result that came out of Gaia as well. We learned was that the Milky Way had an event that we didn't even know about in its early days. So right after the Milky Way formed, probably 13 billion years ago, just a short time after that, it's shown like right away, ringing like a bell out of the Gaia data, that we merged with another galaxy. And it was such a beautiful discovery. They actually named this merged galaxy after Gaia. It's called the Gaia Enceladus galaxy. It's not fictional. It's a galaxy that we think came in, slammed into the Milky Way. They merged. We see the signature of that merger in the way stars are moving around, and also in the chemistry of the stars. So you're taking a three-dimensional map, adding it on to all the other stuff we know about stars, what they're made of, like how much of one element versus another that they have in them. And what comes out like a giant red flag is something happened 10 to 13 billion years ago, and it was bad or good, depending on how you see it. A merger of two galaxies that led to who and what we are right now in this galaxy. That came out like immediate out of Gaia. That was one of these like striking results that everybody saw, and they were like, what? Are you serious? So that one was cool. There's another one too in galactic dynamics. You can see also ringing like a bell through the Gaia data set when you take the 3 dimensions of stars and add them to the motions. We have a dwarf galaxy called the Sag dwarf galaxy. It's kind of orbiting the Milky Way. And the Sag dwarf galaxy has interacted with the Milky Way in also a pretty big way more recently, just about 1 billion years ago. And it has thrown these stars outside of the galaxy, and we have these amazing tidal streams that are ringing up and below the plane of the Milky Way. And you're seeing the resonance in the motions of stars that also, I say it ringing like a bell because it's almost like a wave of motion that you see that's very clearly the result of an interaction between two galaxies. So it's just like you're a detective and you're sleuthing through this data to see what happened, like a cosmic car crash. And you are the forensic evidence, you're running through the forensic evidence, and Gaia is giving you all the data you needed to solve the mysteries. And there's way more mysteries to still be solved. So these are a couple of the ones that I love. There's a couple of things that motion tells us. If you look at a population of stars, say 1.4 billion of them, and you were to look at all of them together and look at all of their total motions together, you can take the linear motion and just look at the distributions. How many fast things do you have? How many slow things do you have? How many things does it show a regular distribution, like what we would normally call like a Gaussian or a bell curve? Or are there a lot of things in the tails? Lots of fast things and lots of slow things. So you can take the motions, and now we have 1.4 billion, and you can look at all those linear motions. And what we've kind of recovered in past studies, and it's definitely ringing true from Gaia, is that stars, when they're born, they move slower. They're still in their natal environment. They're in their like baby nurseries. They're born, and they're given a motion. They're moving around the galaxy, but they haven't had this like what we call kinematic heating or kicked around thing that happens as you move around the galaxy and you interact with giant molecular clouds or other stars. So as you move around the galaxy, you actually get kicked around and your velocities increase. Not as good to try this for an individual star. The way you do it is to grab populations because it's a statistical argument that gets made. So what you can see from the origin of this question of the origins of stars is that you can look at the velocity distribution and the dispersions, or, how far from the median average value stars are, and you can break that down to the young stars and the old stars in the galaxy. And actually, in looking at it this way, it's how they recovered many of the stars that are in what's called the Gaia Enceladus merger, by seeing them having broken apart. Oh, the other thing in this, though, is you can take the motions and you can find who's moving with who. Like friends of friends kind of thing. Sometimes it's family members, they were born together and they're just moving together. Other times it might be a captured object. And so that's something that is very interesting to look into from the Gaia perspective. You can also look at objects that are getting kicked out. They're launched out of the Milky Way. That could be because they got kicked out by the supermassive black hole at the center of the galaxy. It could be because they got tossed out by the large or small Magellanic Clouds, and they're racing through the Milky Way right now. There's lots of reasons for that. So the motions also give you this information about family members, who's moving with who, and also who's out, who's getting kicked out. It's everything from asteroids, because one of the things that Gaia has given you is a map of the stellar positions that is better than any map we've ever had of exactly where the stars are in the sky. And so if you want to know when an asteroid is going to occult, is going to pass in front of another object, you need to know exactly where the stars are. And so asteroid miners, or people that study asteroids, are looking at this very carefully. They're using the star field. So that's from stuff as close as just outside of the Earth's orbit to things that are unbelievably far away. People that are studying quasars, the quasi-stellar radio sources, these objects that are very far away galaxies that have supermassive black holes at their centers, and they're very, very active. So they're using Gaia to calibrate off of those and to find new lensed quasars that you can pull out of the data. And then it's everything in between. And Gaia didn't just measure the stellar positions and motions for stars in our own galaxy. It actually did it for other galaxies, the large and small Magellanic Clouds, the galaxies that are orbiting the Milky Way, and many of the dwarf galaxies that are in the local group around the Milky Way. So just from we didn't just do the Milky Way in this map. We actually did other galaxies as well. And the science stretches from as close as the Earth to as far away as the most distant things that we know about in the universe. And there's no area of astrophysics that is not impacted by Gaia. When it gets into more crowded regions, most crowded regions are the plane of the Milky Way, moving yourself towards the center of the Milky Way when you have the highest density of stars. You can just go outside and see that with your eye. Or in the vicinity of the large and small Magellanic Clouds, which are these very dense areas of other stars outside of the galaxy. So Gaia gets confused in those areas. And that remains a problem in the data, which there are an enormous number of flags that Gaia gives you that indicate how you could work through obvious problems. So I usually show a video when I'm giving a science talk, which shows people this very quickly, in that if you actually open up Gaia and sort of novicely decide, I'm going to go find something. And that's what I did on day one. I was like, I'm going to find the closest thing that Gaia found. It's going to take me 1 minute, and I can't wait. So I'm just going to open it. It's measuring distances. What's the closest thing that no one knew about before? Because if you're going to give me a distance catalog, I bet you found something. So I opened it up, and Proxima Centauri, it was there, it got it, and there were 1,000 objects closer than Proxima Centauri. And it was like, what? Everything is wrong in this catalog is what my immediate thought was. But no, the thing was all 1,000 of those are in the galactic plane, are just confused sources. And there were 2 flags that I could put immediately in that Gaia had given me that eliminated all of those. An hour later, I found an object, and it remains the closest discovery that's been made thus far with Gaia, outside of an asteroid, something outside of our solar system. I found an object that's about 30 light years away that no one had seen before. So there was a discovery. It was made pretty quickly. Anyway, the errors, though, with Gaia remain in the confusion in areas that have high densities of stars. So that's still a problem. And to go down a rabbit hole would take a lot of time. If you really wanted to go into the scientific issues in some of the data, there are intricacies you have to be careful with depending on the magnitude of the object that you're looking at, the area of the sky that you're looking at. So there are words of caution that do remain in the data. But as far as a catalog goes, I have never seen such a successful catalog of objects for which everybody could just jump right in with knowing a couple of flags and words of caution and do science so quickly.